Hello everyone. In the today's lecture, we will discuss about the fixed bias common emitter amplifier circuit. Okay, the small signal model of this fixed bias common emitter amplifier circuit. So now you see here, this is the common emitter configuration circuit where the input is given for the base terminal and the output is taken at the collector terminal. Okay, and the emitter is common for both input and output. So this is fixed bias because you are drawing a fixed amount of current from the resistance RB by fixed voltage. Okay, it is basically fixed voltage. So now to do the small signal model of this, so first we will have to represent this in a two-port network. So now I will draw the small signal model of or not. This is beta RE. Okay, so this is beta RE and this is base terminal, this is collector terminal, and this is emitter terminal which is connected to ground. Okay, so this is the small signal model of the transistor alone. Okay, having base, collector and emitter. So now continuing with this, you have the additional component which is RB and RC. So the RB is connected from where? Base to the 12 volt supply, but here before writing the small signal model, so we have to follow the procedure, that is all the DC supply should be shorted and all the capacitor should be shorted. Okay, so this two important procedure what we have to follow. With this, what happens? So the capacitors are shorted and this two will be connected to ground now. Okay, so this is my input and this is my output. This is RB and this is RC. So you have this RB connected from base to connected to ground. So this is also connected to ground, hence I can connect this RB from base to ground, and similarly collector RC from collector to ground. So this is also connected to ground, so I can connect this RC from collector to ground. Okay, so this is the current source which is beta times IB. This is IB, right? So this is the complete small signal model of the given circuit now, that is fixed bias common emitter amplifier circuit, right? And corresponding to this, we are giving the input for the base terminal. This is my input between base and emitter, and this is my output from collector to emitter. Okay, so this is my IC. Fine. So now to find out the input impedance Zin. So input impedance means it is with respect to input voltage and input current. Okay, so input voltage and input current. So here when we see between these two terminals, what is the procedure? All the voltage source has to be shorted and all the current source has to be open. So all the voltage source means this is the output voltage what we do, so output is shorted. When this is shorted, the RC will also becomes neglected and this current is made open circuit. So the current, this is completely made open circuit. This R0 is again open circuit because it is a large value. So only thing you have left is so RE, beta RE and the resistance RB. So only these two resistance will be effectively found between these two terminals at the input voltage. So Zin will be RB parallel with beta RE, that is our input impedance, right? And equation 1, output impedance. To find out output impedance, it is the impedance seen with respect to output terminal, these two terminals, right? And again with the procedure, when you are finding the output voltage, all the voltage source should be shorted. So corresponding to this, at the input side, V in will be shorted. So V in will be shorted. So because of V in is shorted, RB will also get shorted and beta RE will also be get shorted. So this entire thing will be connected to ground, and here at the output side we have the current source to be open, which represents infinite resistance, and R0 and RC. Okay, so when we see from this output terminal, we have only RC parallel with R0, right? So this is our output impedance corresponding to equation 2, right? So now to find out the gain, we will consider the output voltage. Output voltage is equal to output current into output resistance or output impedance. So you see here, this is my output voltage, this being plus, so corresponding to this will be my I0. So now I0 is nothing but IC in the opposite direction, so this I0 I can write it as minus IC and Z0 is RC parallel with R0. Okay, so this is my V0, and IC, we know that IC is beta times of IB. Okay, so IC is nothing but beta times of IB. So IB is V in by Z in. So yeah, input voltage, input current IC, input current IB is nothing but input voltage by input impedance Z in. So I can write this as V in, and what is the Z in we got? RB parallel to beta RE. Beta RE parallel with RB. Okay, so this is my IB. So substituting in here, you get IC equals beta times of V in by beta times RE parallel with RB. So this resistance what we have, the input impedance will be approximately equal to beta RE, because the value of RE is anyhow small, which is an equivalent value of the diode resistance. Okay, and we have to calculate that RE, we will do that later. So now this is the expression for equivalent expression, that means approximated expression for Z in. I can write it as beta times of V in by beta times of RE. Okay, this is my IC. So substituting it in here, V out is equal to minus beta times V in divided by beta times RE into RC parallel with R0. So effectively again this RC parallel with R0 at the output impedance, this will be equal to RC, only RC, approximately equal to RC, because R0 is the large value. So even though R0 is large resistance parallel with the small resistance, effectively equal to RC. So this I can write it as V0, and taking this V into the denominator, V in is equal to minus RC by RE. So this is the expression of voltage gain. And considering the current gain, output current IC divided by input current IB, which is equal to beta, this itself will be the current gain AI. Right? So this is the AC analysis for which we calculated the input impedance, output impedance, voltage gain and the current gain. So these are the AC parameters of an amplifier circuit for this fixed bias common emitter configuration. These are the expressions what we have got. So now solving the same for the numerical value what they have given, 240K, 2.2K, 12 volts and beta is not given, we will take beta as 51, and r naught is not given, we will take this r naught by default as infinite. Okay, so now solving for this, again, fixed bias, this is 240k, this is 2.2k, this is 12 volt, beta is 51. Okay, so now to find out the IB here, IB is obtained by applying KVL at the input loop. This is my input loop what I have. So in the input loop I have this VCC 12 volt distributed across this RB, resistance RB, and you have VBE connected to the ground. This is VCC plus minus, this is plus minus plus minus, this is VBE, the base to emitter voltage, which is by default taken as 0.7 volt. Okay, so now applying KVL to this loop, we get VCC is equal to this current flowing, this is IB into RB plus VBE. Okay, so this is my equation. So in this I have to get expression for IB. So IB is equal to VCC minus VBE by RB. So this is VCC is 12 volt, VBE is 0.7, and the RB is 240 kilo ohm, right? So solving for this, you will get IB around how much? 47.08 microamps. So this is my IB. So once I get my IB, I can calculate IC, which is beta times of IB. So beta given here is 51. 51 into IB is 47.08 microamps, right? So this is my IC. So on solving this, I will get IC as 47 into 51, I see approximately around 2.4 milliamps. So this itself will be your ICQ. Okay, and to find out VCEQ, we will apply KVL to the output loop. Okay, so this output loop what we have, I will write the equivalent circuit of the same. So this is RC, so this is VCC, and this is VCE. So the emitter is connected to ground, this is VCC. Okay, so now this is plus minus plus minus plus minus. So now applying KVL for this output loop, okay, KVL to this output loop, we will get the equation VCC equals ICRC plus VCE. Okay, using this you will get the equation directly, VCE, which is equal to VCC minus ICRC. So you can substitute the value 12 minus IC is 2.4 milli and this is 2.2 kilo ohm. You will get it around so this is around 5.2 volts. 12 minus 5.2, you will get it as 6.8 volts. VCEQ will be around 6.2 volts. Okay, so now substituting for this input impedance for the AC analysis, we have to calculate RE. RE is 26 milli by IE, which is nothing but IC. So 26 milli by IE is approximately same as ICQ. So 2.4 milli, you will get it around 10.83 ohms. 10.83 ohms. So now writing the equivalent small signal model for this. So this is 240 kilo. So this is beta Re. So beta Re will be 51 into 10.83 ohms. So beta Re will be around 500 something greater than around 510 ohms. I'll take it as 510 ohms beta Re. So this is 510 ohms, and at the output you have this IC, which is beta times I. R0 is not given, so this is RC, which is 2.2k. okay, so corresponding to these equation, what we have got, that is, so RC is equal to, Z0 is equal to RC, Zin is approximately equal to beta Re, and AV is minus RC by Re. okay, so now Zin is approximately equal to beta Re, which is around, Zin is around 510, what we have written, 510 ohms. Z0 is approximately equal to RC, which is 2.2k. AV is much, expression for that is minus RC by small Re. So this RC is 2.2k by Re is 10.83. so you will get around 203.14. so this is minus 203.14. okay, and the current gain AI is nothing but IC by IB, which is beta, which is equal to 51. so this is the current gain. So the minus indicates here that the output is out of phase with respect to input. So if this is your input going from high to low initially, so the output here will be going from low to high, reference to low initially, and when the input is going low, the output will be going high. So it indicates that output is out of phase with respect to input, and the magnitude of this will be equal to 203 times, 203 times of 203 times of input, 14, right? So this is the small signal model for the fixed bias common emitter configuration circuit. okay.